Good morning, children. Welcome to class 12 online chemistry class. Today I'll give the video tutorial of properties of alcohol. First, let's see the physical properties. And as you know, we have a particular type of question, the assertion reason type of question. So in this form only I wrote the entire physical property. Left side we have the statement or declaration, that is assertion, and the right side is its correct reason. So let's first start with the physical property. All alcohols have higher boiling point than the corresponding hydrocarbon or ether or haloalkane with comparable molecular mass. That is, if the molecular mass is equal or nearly equal, what we will find that alcohols are having a higher boiling point, and that is due to the ability to form intermolecular hydrogen bond. The next one is boiling point of alcohol will increase with increase in carbon number. It's obvious that as we go to the higher and higher homologues, the boiling point increases. That is due to increase in van der Waals attraction with increase in mass of the molecule as well as the size of the molecule. The third variation of boiling point that is observed is the primary alcohol has a higher boiling point than secondary alcohol, which has a further higher boiling point than tertiary alcohol. That means for this isomeric alcohols only, the boiling point decreases with increase in chain branching, because what happens in increase in chain branching, the surface area decreases. In case we have 1, 2, 3 and 4 and 5, that is simply the pentanol. If this pentanol would be your 2-pentanol, that means if you'll write it like this, pentanol, it's obvious that its surface area is slightly more. And in case we have a tertiary one, further the surface area decreases, and thereby what we can say for this case, if the surface area is decreasing, the van der Waals force will also decrease, and that's why the boiling point decreases even if the molecular masses are same. The next one is its solubility. So lower homologue of alcohols are completely miscible or soluble in water, because this alcohols and water are able to form intermolecular hydrogen bond. The higher members are less soluble in water, because this R will be hydrophobic, and that R is more prominent in comparison to this OH, the presence of this polar OH part. So this, due to increase in this alkyl group or hydrophobic part, the solubility decreases. Alcohols have a narcotic action, because this can act on central nervous system that affects the judgment and also lowers the inhibition. Chemical properties of alcohol. Alcohols have versatile nature because of the two particular bonds, the CO bond and OH bond. That means it can react in three ways. One is through the cleavage of CO bond, one is through the cleavage of OH bond, and one is by using this unshared pairs of electrons. Now let's see, in this way alcohols can behave as an electrophile as well as an nucleophile. The protonated alcohols behave as electrophile. So when this H plus adds to the unshared pair of oxygen, it forms the protonated alcohol. This protonated alcohol, because of this plus, acts as an electrophile, and therefore it's obvious that the bond is being cleaved. That so any reaction in which that CO bond is being cleaved, it undergoes a bond cleavage of CO bond, and that is a electrophile reaction. We have certain list of the reactions as a reaction with any chlorinating agent, for example PCl5 or PCl3 or red phosphorus and bromine, red phosphorus and iodine, or the thionyl chloride SOCl2, the best chlorinating agent. Might be the Lucas test, in which we have the HX and anhydrous zinc chloride, that is also used to detect the presence of alcohol, and is the dehydration, whether it is intermolecular dehydration or intramolecular dehydration. Intermolecular dehydration leads to the formation of ether, while intramolecular gives the alkene as the result, and this dehydration is actually beta elimination guided by Sedzev's rule. Coming to alcohols as nucleophile, it could be of two ways. Either it will involve the fission of OH bond. So if OH bond is cleaved, it is the release of H plus and RO minus, that is alkoxide ion. So it is actually the acidity of alcohol or acidic property of alcohol. The supporting reactions are reaction with metal, reaction with Grignard's reagent containing the active hydrogen, and esterification reaction. We also have the reaction of alcohol due to unshared pair of oxygen. That is, the reaction to unshared pair of oxygen is supported by catalytic dehydrogenation or dehydration and the oxidation reaction. First reaction, acidity of alcohol. This acidity of alcohol is due to the polar nature of OH bond. Any factor that will facilitate the splitting of OH bond or polarity of OH bond will enhance the acidity of alcohol. Let's consider the primary, secondary and tertiary alcohols. The presence of electron releasing group, that is the alkyl group, increases the electron density on oxygen. So all these provides the higher electron density on oxygen, and greater is the number, of course, that greater electron density would be there in oxygen. So polarity of OH bond will decrease and acid strength will decrease from primary to tertiary alcohol. That is, the most acidic is primary, followed by secondary and then tertiary alcohol. In this context, certain things has to be noted. The bond cleavage of OH bond will be fastest in primary, followed by that in secondary and then in tertiary. The supporting reactions are first reaction with metal. So when this alcohol is treated with sodium metal, it first forms sodium alkoxide and nascent hydrogen. That's why the mixture of sodium and alcohol acts as a mild reducing agent. When this alcohol is treated with metallic sodium, in this ratio it forms H2 gas, that is, the effervescence is observed. This is also used as one of the chemical tests to detect the presence of alcohol group. To avoid this explosion, as this alcohol solution is being taken in water, we use calcium chloride as the safety measure to absorb the moisture or water present in alcohol. If this alcohol is treated with aluminium, it forms trialkoxy aluminium with the liberation of hydrogen. I have shown an example with tertiary butyl alcohol. We will get tri-tertiary butyl aluminium along with hydrogen. This is the reaction of alcohol with metal to show the evidences of its acidic property. The next acidic reaction is esterification reaction, and as we know, it is the reaction between an alcohol and an acid and an alcohol in presence of concentrated sulfuric acid. It is a reversible reaction. We will get ester as well as water. There are certain points regarding this esterification reaction. Please do try to write all such points. One is, this esterification also takes place in presence of dry HCl gas, dry hydrogen chloride gas. The second important factor is the reaction is reversible, so immediately we have to remove the water formed just to avoid the backward reaction or to get a better yield of this ester. Even a better yield of ester could be observed when this is treated with acid chloride. Instead of acid, we use acid chloride, and pyridine is used and dry HCl, so that the pyridine absorbs HCl and neutralized, and therefore we do not get the chance of backward reaction. The supporting evidence of the reactivity of alcohol in the order of primary followed by secondary then tertiary as an acidic property is evidenced by the esterification yield. Primary alcohol gives 85% of ester, secondary alcohol gives 67% of ester, and tertiary alcohol leads to only 22% of the reaction. This esterification carried out in presence of dry HCl gas is known as Fischer-Speyer esterification reaction. That's all about the esterification reactions. Do write this all important factors. Now come to the next reaction, the reaction with Grignard's reagent. Alcohols are active hydrogen containing compound, and this hydrogen is active, so this hydrogen could be eliminated with this alkyl group R, forming alkane along with the magnesium salt. So therefore, when preparation of alcohol is preparation of any of the functional group is carried out in by taking Grignard's reagent, we avoid the presence of moisture, presence of alcohol, all these, and that's why dry ether is used as the medium to make it free from alcohol or any of the active hydrogen compound. Nucleophilic nature of alcohol, the second property, it depends upon the bond cleavage of carbon-oxygen bond. This bond will be cleaved. The order of reactivity is tertiary alcohol maximum, followed by secondary alcohol and then primary alcohol, just reverse to the acidic property. The supporting reactions are reaction with phosphorus halide, that is either PCl5, PCl3 or PBr3, PI3. In fact, PBr3, PI3 is not existing. They are formed in situ, as we have already seen this in haloalkane haloarenes chapter, or chlorinating agent or any of the halogenating agent. The first reaction is with PCl3, when we will get haloalkane along with this, or chloro derivative along with this. The derivative side product is H3PO3. PBr3 or PI3 is bulkier and therefore not stable due to steric factors. Therefore, we are supposed to prepare PBr3 or PI3 in situ. For this, we take red phosphorus and bromine, or red phosphorus and iodine, where this is formed RBr or Ri along with again H3PO3. When PCl5 is used, the side products are HCl and POCl3. But we know the best chlorinating agent is still thionyl chloride, because this is leading to escapable gases as the side product, and the RCl we are getting, that is in the purest form. The next supporting reaction is Lucas test, that is the reaction between alcohol and HX in presence of anhydrous zinc chloride to give the RX or halogen derivative in presence of water. Now, since alcohols and HX both are soluble in water, so the reactant is just in aqueous medium, while one of the product is partly soluble and therefore appears as milky or turbid solution. So the showing of this turbidity actually determines the extent of reaction. When ROH, that is alcohol, is treated with HCl in presence of anhydrous zinc chloride, it forms RCl and water. So if we observe instant turbidity, we will see that this is tertiary alcohol. If turbidity appears after some time, it is secondary alcohol, and if turbidity is shown only on heating, it is primary alcohol. This again supports that tertiary alcohols are most reactive towards this CO bond cleavage, followed by secondary alcohol and then primary alcohol. One more important thing needs to be told here, that even the primary and secondary alcohol sometimes needs the anhydrous zinc chloride as the catalyst, but tertiary alcohol even doesn't require this catalyst. Just simple shaking of this alcohol with HX leads to the formation of turbidity with tertiary alcohol. Next, come to the third type of reaction in the CO bond cleavage. This is dehydration reaction, which is actually evidenced as intermolecular dehydration or intramolecular dehydration, that is within the molecule, and one is in between the molecules. So the reaction occurs as ROH, two such units in presence of concentrated sulfuric acid. Our temperature is less than 140 degrees Celsius when this elimination of water occur, and we are getting ROR, usually the symmetric ether. This is how intermolecular dehydration occur. In intramolecular dehydration, that is within the molecule, this is as per Sedzeff's rule. We take concentrated sulfuric acid to a greater temperature to 140 degrees Celsius when a beta elimination takes place, and we will get alkene as the product. If we have CH3, CH2, CH2, CH3, 2-butanol, this in presence of concentrated sulfuric acid beyond 140 degrees Celsius will follow elimination as per Sedzeff's rule. It has 2 beta hydrogen, but it is a regioselective reaction where we will get the 2-butene as the major product. More substituted alkenes are more stable. Now in both the cases, dehydration occurs, but this dehydration is actually taking place through either in between two molecules or within the single molecule, including the beta hydrogen. Let's come to the last one, and these two reactions are having the mechanisms also. We will also discuss the mechanisms. Now we'll see the next reaction, that is the reaction of alcohol due to unshared pairs of oxygen. This is one of the nucleophilic property of alcohol. Now in this reaction we have the supporting evidences. This unshared pairs act as nucleophile. The first supporting reaction what we observe is its oxidation. Now this mechanism of oxidation is not there. We see generally primary alcohols on oxidation gives aldehyde and secondary alcohols on oxidation gives ketones. Now using this there are certain points of differences. Let's see what are the points of differences. The primary alcohol mainly needs a mild oxidizing agent. It could be pyridinium chlorochromate or it could be bromine water which provides nascent oxygen, and in fact we observe the elimination of this 2 hydrogen over here. So thereby to satisfy the valency it has to form a double bond. The pyridinium chlorochromate is one of the heterocyclic derivative. This is pyridine and the lone pairs are now forming one coordinate bond with H plus. This is pyridinium ion and chlorochromate ion is CrO3Cl minus. This is pyridinium chlorochromate. The most important thing in pyridinium chlorochromate or PCC is it does not affect the side chain or anything, only changes the primary alcohol group to aldehyde group, or it only causes the selective oxidation, does not affect the carbon skeleton present other than the specified point of action. If secondary alcohol is there, that is RCR, it requires a relatively stronger oxidizing agent CrO3 in presence of H plus. So this nascent oxygen actually takes up this 2 hydrogen and forms ketone. This R and R dash may be same or may be different. Tertiary alcohols do not undergo oxidation due to absence of any alpha hydrogen. However, at elevated temperature and strong oxidizing agent, tertiary alcohols at times forms carboxylic acid with lower number of carbon. Even one more point, primary alcohols when treated with a strong oxidizing agent, suppose KMnO4 or K2Cr2O7, it forms directly the carboxylic acid. The next reaction, supporting reaction, is catalytic. Dehydrogenation or dehydration. In this reaction, we use copper metal at 300 degree Celsius. This is the reagent. When we use primary alcohol, this copper at 300 degree Celsius takes up this 2 hydrogen and forms RCHO. When we take, it is a secondary alcohol, copper further takes up the alpha hydrogen and forms ketone. So these two are dehydrated dehydrogenation reaction. But since tertiary alcohol is not having any such alpha hydrogen, we are considering a tertiary alcohol, tertiary butyl alcohol. To the presence of this groups, it is not having any alpha hydrogen. So how does it react with copper? It takes up this beta elimination and forms an alkene. So this reaction is actually a dehydration of tertiary alcohol. That's why in presence of catalyst, we are writing it as either a dehydrogenation or a dehydration reaction. The primary and secondary undergoes dehydrogenation reaction, while tertiary, in absence of any alpha hydrogen, undergoes dehydration reaction and forms the corresponding alkene. Mechanism of dehydration of alcohol. Intramolecular dehydration or beta elimination take place above 140. In fact, above 140 a carbocation is formed. So in first step, the protonation to unshared pair on oxygen of alcohol would occur. It requires dilute sulfuric acid, concentrated sulfuric acid, which breaks up to H plus and HSO4 minus. This H plus acts on the unshared pair. It's a fast process and forms protonated alcohol, also known as oxonium ion. This protonated alcohol go a slow dehydration process and forms a carbocation over here. Since it is the slowest step, it is the rate determining step also. So once this carbocation is formed, after that it takes up the hydrogen, releases hydrogen and takes up the bond to form the corresponding alkene. And H plus so formed takes up the conjugate base HSO4 minus and forms the sulfuric acid. Intermolecular dehydration of alcohol, that is alcohol to ether mechanism. When we take 2 moles of ethyl alcohol or ethanol below 140 degrees Celsius, we get diethyl ether and water. The reaction is actually SN2 mechanism and carbocation is not formed. So it forms the transition state as intermediate. So what we get here, the first step is exactly same, protonation of alcohol by this unshared pair of electron. It forms the protonated alcohol or ethyl oxonium ion. After that, instead of this dehydration, it undergoes SN2 reaction. Now see, the second alcohol molecule uses still its unshared pair and a simultaneous bond cleavage of this carbon oxygen and a bond formation of carbon oxygen also take place. Thereby we are again getting a protonated species. This protonated species or oxonium ion on deprotonation releases this H plus and we get an ether. That's how the whole reaction is being taking place. So in the next class we will discuss with other features of this reaction and the formation of ether and the reactions of ether. Thereby we will be able to complete that particular chapter.